So hello everyone and welcome to today's session. I hope you can all hear me. Thank you for joining us. Today you will be learning from our expert David Williams about how to increase reliability and profitability in the delayed coking unit with continuous level measurement. I'd like to introduce today's presenter. David joined the US Navy out of school and was accepted into the US Navy nuclear power program. He spent 10 years operating nuclear reactors for propulsion in the Navy. After which, David took a job programming PLC for automation control and finished his degree in nuclear engineering technology. After 3 years of programming experience, David was hired by OMART as a field engineer. And after 8 years in the field with OMART Vega, he spent 10 years using his expert knowledge of different process technology, not only to advise employees, but operating companies in the proper use of nuclear level and densities in process control. David has been with Berthold Technologies for 2.5 years. After the presentation, there will be a question and answer round where questions you enter to the chat or the Q&A function will be read out to and answered by David. So please use these functions to send us any questions you may have. A recording of the webinar will also be available. So we may start, and we hope you enjoy today's event and find it interesting. Afterwards, a survey will pop up. Please fill it in to help us and we can learn from your feedback. So with this, I'll pass over to David.
Thank you, Carrie. Hopefully everybody can hear me. I'd like to thank everybody for taking time out of their schedule to join us and take the time to watch and maybe hopefully learn. So as Carrie mentioned a little bit about my experience, I want to expand upon that a little bit more to give a little bit more detail about my experience with delayed coking. So when I started working with nuclear gauges about 20 years ago, one of the first things I worked on was delayed coking. And without understanding how the delayed coking process worked, I was naive enough to fully believe that the equipment that I was working on was 100% the best thing ever. And slowly over time, understanding the process, understanding how the nuclear gauges work, I was able to come across and understand there's some things slightly different in a delayed coker versus other nuclear level gauges that you might find in a refinery. So I've been involved in the startup of over 45 grassroots delayed coking units and revamps over 60 more over the past 20 years. I've been to 125 delayed coking units around the world to advise on the nuclear levels, not only the continuous level systems using gamma radiation, but also the neutron backscatter systems. So I have this unique situation to not only learn about the process of delayed coking, but also through all the data I've been able to collect over the years and my experience, I've been able to use this knowledge and correlate it for some unique understandings of what's happening inside the drum with the foaming and particulate matter. Using this knowledge of the process and understanding what's happening with the foams inside and my knowledge of how the nuclear gauges actually work has allowed me to make tweaks to the level system so it can make a more accurate and more reliable measurement. So it went from a standalone single gauge to a complex system of individual gauges working together to give you an output. So this is some of the experience I have over the last 20 years. I've been working with measuring radiation for over 30 years now. So I have a pretty good understanding on how to detect radiation and what does that mean. So to get started in the presentation, so the first thing is the agenda. What are we going to talk about? I'm going to spend the first couple minutes talking about who is Berthold, what do we do, where are we located. Then we're going to talk about the two main measurement technologies that are used in measuring level inside delayed coking, which is neutron backscatter and the gamma continuous level system. Then we're going to talk about the drum level measurement itself. Why is it unique? Why is it different than, let's say, a vacuum top bottom or any other level system that you might see in a refinery? And then we're going to talk about how we actually make that measurement, what components are entailed in making that measurement. And then we're going to talk about some of the benefits, some of the realistic goals that you can get by using the continuous level system. And then we're going to talk a little bit about some issues that you might come across by using the gamma system. So who is Berthold Technologies? Berthold Technologies is a company based in Southwest Germany. We've been specializing in radiometric devices, nuclear gauging, since 1949. So we're the worldwide leader in selling and producing nuclear gauges around the world. And we also have subsidiaries around the world to help support our customers. So they're physically located throughout Europe, Asia, United States. In the countries where we don't have a subsidiary, we have large representation companies that will support our customers. We have over 350 employees worldwide. So as you see on the slide, we have offices in the US, United Kingdom, Norway, China, India, Italy, France, and of course, Germany. So how did we get to where we are today? It all started back in 1949 with Professor Dr. Rudolf Berthold. He was working with BASF, and he developed the first nuclear level switch on a process vessel they had there that they was having issues with. So some of the things that is in this timeline that you see over the history is in 2003, we developed the SuperSense, which is the most sensitive detector on the market. This allows us to use very low source activities or replace existing detectors and keep using the existing source for several more years after the fact because of the extra sensitivity this detector affords us. And the other big thing we have is SIL 2, SIL 3 on our detectors, not only on continuous level detectors, but also on density gauges as well too. So, and then since we have this history going back to 1949, 1950, we have over 70 years of experience with all of our knowledge that we have, with all the individuals we have working around the world. We basically have a lot of experience with process technologies, different industries, be it chemical, be it paper, be it glass, that if you need help and need assistance and make it a tough, challenging application, be advised that we can help you and make that measurement and make it nice and reliable so you can control with it. So one thing we're going to talk a little bit about is nuclear gauge history. Where did everything started from? So you see over here in 1949, Berthold started. Some of the first companies that started, Olmart started in 1951. Nuclear Chicago started in 1954. Texas Nuclear started as a research lab in 1956. The reason why I bring these names up is because these are the ones that are predominantly in detecting of the coke drum systems now. So you see Nuclear Chicago started, they merged with Texas Nuclear for a while in 1961. And then they got bought by another company. And in 1974, Nuclear Chicago spun off Carryover. So Carryover was one of the main providers of neutron backscatter for delayed COKING for a long time. So later on in the history, during this time frame, Texas Nuclear also provided neutron backscatters for the delayed COKINGs. So Texas Nuclear becomes Thermal Measure Tech in 1994 when Thermal Electron buys them. Thermal Measure Tech 2 years later ends up buying Carryover. So this consolidates the two major manufacturers of neutron backscatters into one company in 1996. So that's the one thing I want to talk about, is that now there's only one vendor of the neutron backscatters being used for the delayed COKING purposes. And then late last year, October of last year, Thermo Fisher Scientific announced they discontinued the nuclear product line. So the manufacturer of the neutron backscatter gauge is no longer in the market. They're going to be supporting the systems for another 4 years. They took the last order in January 31st, 2020. So they're no longer providing gauges into the industry and stuff. The other one that is major in delayed COKING is Olmart. So Olmart got bought by Vega in 2011. In 2012, the Gen 2000 electronics has been obsolete, and they're going to support that until 2021, 2022. So this is just a timeline of predominantly the gauges that are used in the nuclear coke, the coke drum systems. So where else are we at in the industries? We do chemical, petrochemical, steel, coal gasification, pulp and paper, glass. So anytime there's a tough, difficult, challenging application where it might be a high temperature, high pressure, it's something that might coat, that might cause displacers or differential pressure measurement levels issues, which where the nuclear gauges actually work really, really well. So our experience, what's our experience around the world? In the refineries, we do measurements on desalters. We do it in crude towers. When I talk about crude towers, that means fractionation towers like coker fracs, FCC fracs. It could be vacuum towers, the main distillation towers. Anytime that there's heavy oil on the bottom of the measurement, the nuclear gauges work relatively well since they're not susceptible to ports or bridles being plugged. Delay cokers, of course, solvent deasphalting units, alkalizations. We can do the acid rerun column. We can do the depropanizer. We can do the settler. We can do the acid dump tank. We also do resid hydrocrackers, be it ablated bed or slurry hydrocrackers. FCC units. We can do the reactors. We can do the precision hoppers, cyclone separators, and then also the CCRs for the lock hoppers and stuff. But today we're going to focus on the delayed coking units. So where do we have our experience around the world? So we have a lot of our equipment in Brazil, the United States, Russia, China, India, and Europe. And that makes logical sense since we're a European company. We do have a lot of business in the European, in Asia. So some of the companies that we've done work with in the past, OMV, Eni, BP, Round Patrol, SR, Sinopec, ExxonMobil. So these are some of the big name producers and refiners around the world that we do have level equipment on the delayed coking. So I'm going to talk a little bit now about how nuclear gauges work. So just a brief understanding of what they do, how they measure, and that way you can hopefully understand a little bit later on in the presentation what we're talking about. So on a neutron backscatter, the main thing I want to take away from this slide is that it is several different interactions happening at one time to spit out a neutron. That neutron's important is because that's what's actually making a measurement. Two things has got to happen on that neutron is that it's got to leave the source, go inside the vessel, hit an object, and scatter back, hence the name backscatter. But something else has to happen in order for that to be detected. On the way to being scattered back, it has to also be thermalized. Thermalized is a fancy word that basically means that that neutron's got to slow down. So the one thing that's really, really good at slowing down neutrons is hydrogen. So a neutron backscatter is more commonly referred to as a hydrogen density gauge than it is a level, because it does not necessarily measure a level. You can infer a level by the change in hydrogen concentration, but it is actually measuring the hydrogen concentration in front of it. So here you have your americium and beryllium source, and then you have your detector all in the same housing mounted on the side of the drum. And then it emits neutrons into the vessel. So that neutron goes in and hits a hydrogen atom. Since a neutron is a neutron and hydrogen atom is a proton, they're the same physical size. So it gives off a lot of energy when that collision occurs. So therefore it is slowing down. It is being thermalized at that point. If it hits a carbon atom, which is 6 protons, 6 neutrons, that is 12 times larger. It bounces off basically at the same speed. So a lot of its energy is not transferred. So therefore it does not get thermalized. So more hydrogen in front of it, more neutrons get thermalized, the higher the reading that you get on the device. So the important things to remember is that it is directly proportional to the radiation value. The higher the radiation, higher the output. And that higher the output refers to more hydrogen, not necessarily more level. And we will talk more about that later on. So when you're talking about gamma continuous, you consist of sources mounted on the outside of the drum, and then you have detectors mounted on the opposite side of the drum. So we are transmitting radiation from one side of the drum to the detectors on the other side of the drum. So we are giving you more of a cross-sectional average what's inside the drum. The one thing I forgot to mention on the neutron backscatters here is that you see this little sphere I have inside. This neutron backscatter gauge only basically measures in this small little sphere of influence. Once the neutron gets outside the sphere, it does not have a more likely chance to get scattered, come back into the detector to be detected. So it's only basically measuring what's inside the sphere, about 18 inches in, 18 inches up, 18 inches down, about 450 millimeters in, up and down. So this gives some rise to some issues. We're going to talk a little bit later on about some reliability issues that neutron backscatter gauges may have. So with the gamma continuous, the sources being on one side and the detectors being on the opposite side, it's a transmission. So anything in between the vessel and anything inside the vessel in between the source and the detector gets detected. So when the level is low, you have the most amount of radiation to your detectors. So therefore that equals the lowest level. When you have more material inside the vessel, a higher level, you get less radiation to the detectors because this material inside the vessel actually absorbs this radiation. So this energy from the sources does not reach the detector, so therefore no longer detecting a principal amount of radiation. So anything that's in between a low level and a high level, you get a certain amount of radiation to the detectors, and we can infer a level off of that. So one thing that is a misconception out that a lot of people think of is that these things have spatial resolution. What I mean by that is in this picture, you have radiation from basically this blue arrow on up, and between the two blue arrows, there is no radiation from the sources getting to the detectors. So a lot of people think that the detectors can say, hey, I have radiation from this point on up, so therefore I know where my level's at. That's not how the nuclear detectors work. It's measuring the average radiation across the whole length of this detector. So if I was to go out and put a small radiation capsule here, that'll increase the radiation value here. So the level system would actually decrease in value because they would think that my whole level has changed, even though I'm only changing radiation at one specific point on the detector. So there is no spatial resolution on the detector. And that's important to understand later on when we start talking about some advanced functions and features within delay coking. Because if I was just to change the vapor density in this area of the drum, which happens inside the cycle of the coke drum, the amount of radiation to this part of the detector changes. So if this radiation was to decrease due to my vapor density increasing, my level will actually rise, even though the level is still constant here, because it's just measuring that change in radiation. So there is no spatial resolution on the continuous level. So as I mentioned, it's exact opposite of the neutron backscatter. It's indirectly proportional to the radiation. More radiation to the vessel, to the detectors, lower the level inside the vessel. Higher the radiation to the detector, lower the level. Lower the radiation, higher the level. So it's the exact opposite of the neutron backscatter. So one thing that everybody does have a concern about is when we start talking about radiation is it dangerous? What is the effects to it? So I'm going to talk a little bit about dose rates around the individual components if you have them on your delay coker. So here you see an overhead shot of delay coker. Here's the coke drum, outlet nozzle, source for the gamma, detectors for the gamma, and here's my neutron backscatter. So if we zoom in on the neutron backscatter and look at the radiation fields around it, so at 300 millimeters around the detector, you get about 105 microsieverts per hour, about 10.5 millirem per hour. At 1 meter, you get 85 microsieverts per hour, about 8.4, 8.5 millirem per hour around this. So if you look at this picture here, this is a neutron backscatter. You see this yellow sign. In the North American market, we have these yellow signs called radiation areas. That's a defined area where the radiation dose rate is above 5 millirem per hour. So you would see these signs out there next to the neutron backscatter because it is greater than 5 millirem per hour. Other places around the world, they might not use the term radiation area. They might use a term called classified area. So that means you have to take special precautions, limit your time around it, limit your spacing from it, something that you have to do to minimize the exposure that you have because of this. So since I'm talking about radiation values, let me give you a little bit of frame of reference. So here you get about 8.5 MR at 1 meter from this detector. So you get about 16 millirem total dose when you get a chest X-ray. That's instantaneously in a split second. So around this neutron backscatter, you would have to sit here for about 2 hours at 1 meter to get about the same amount of radiation that you get on a chest X-ray. So the radiation fields around this, yes, it's higher than that 5 millirem per hour, but it's still relatively safe. And you can greatly reduce that again by taking a little bit smaller steps away from it, or like I mentioned before, is limiting your time. If you just walk past this and it takes 2-3 seconds to walk past this, your total absorbed dose is relatively low. So now let's look at the gamma on the source side. On the source side, you typically have about 20 to 30 microsieverts per hour at 1 foot around the shield, the source holder. That's about 300 millimeters. And then about 1 meter around it, you have 0.5 to 1.5 microsieverts per hour, which is 0.05 to 0.15 MR per hour. So if you're getting 0.1 MR an hour at this thing, you have to stand here at this 1 meter location for 160 hours to get the same amount of radiation that you get in a chest X-ray. So the radiation that you get around the shield is relatively low. Now I mentioned that as relatively low if you follow the recommended mounting practices. We want to try to keep this shield, this source, as close to the vessel as possible. And the reason why that is, you see this angle as this comes out. Once that radiation leaves the source holder, the shield, it starts fanning out in a beam. If you was to move this thing farther away, that angle hitting the vessel gets wider and it starts scattering back off to the sides. So you want to minimize this distance here. I have seen some locations around the world where this thing is mounted 300, 400 millimeters off the vessel and is creating radiation areas out here due to scattering effects. That scattering effects can be greatly reduced by moving it closer to the vessel. So then on the detector side, a lot of people have this inherent belief that this side is dangerous because the radiation is pointed this way. But radiation transmission is an inverse square. So the amount of radiation that you have on this side is a lot less than what you have on the source side because of the transmission through free air. So if you look at around the detectors, we typically have 0.2 to 0.3 microsieverts per hour, 0.02 to 0.03 millirem per hour around at 1 foot around the detector, 300 millimeters. At 1 meter, it's even less than that, 0.1 to 0.2 microsieverts per hour, or 0.01 to 0.02. So if this is 0.01, now you have to say 1,600 hours at 1 meter to get the same amount of radiation that you get in a chest X-ray. So the amount of radiation that you do have out there is relatively low for both the radiation on the gamma detectors and also the neutron detectors. So what makes a coke drum level different than other applications inside a refinery? Why do we treat it differently? So if you go to a typical level in a refinery, let's say that you have a tower bottom measurement, it's a continuous process. What do we mean by continuous process? You're continuously feeding fluid into the vessel and you're continuously taking processed material out. So you're operating on a continuous basis. Process conditions don't really change that much. The vessels are typically smaller, typically 2 to 4 meters in diameter, 8 to 15 feet in diameter. The lower density stays relatively constant. The fluid density, it might go from 850 to 870 kg per cubic meter, which is enough to affect differential pressure or displacer per se, but not enough to really affect the output of a continuous level using nuclear. So the calibration doesn't really change because the conditions are constant. Conditions are continuously operating. So that's the reason why we really don't have the thing. I like to use the phrase all the time, to use the late night infomercial on the rotisserie oven. You set it and you forget it. You really don't have to mess with anything on these things. And that's why a lot of people like using them on fractionation tower, vacuum tower bottoms, because they're extremely reliable. They don't have to worry about process fluid changes, pressure ports being plugged up or anything like that. But now on a delayed coking, it's slightly different. So on this one, you see a tower bottom. Here is the continuous level mounted on the side of the vessel. So on the delayed coking, on the coke drum, it's a semi-continuous batch process. So what does that mean? That means you have two vessels working in conjunction with each other. As you're filling one, you're basically emptying the other one. So the process, the feed is being constantly fed in, but it's alternately being cycled between two different vessels. And you have that stages that you might have, online stage, offline stage. So your process conditions do change within the cycles. You also have possibility of buildups and stuff. So your calibration data keeps constantly changing, depends on what part of the cycle that you are under. So I created this little chart to help understand the different parts of the cycles that you might have in the delayed coking unit. So you have a cold empty drum where it's just atmospheric pressure inside. So you don't really have an upper and lower fluid phase at that point because it's just all atmospheric. Then you do your pressure test with steam. So you don't have an up and lower. So you go from zero, no change in vapor, to a minus 5% change. So as you increase the steam pressure inside the drum, you reduce the radiation to detectors by 5%. And then you can open the overhead lines to back warm the vessel. So now you emit hydrocarbon vapors inside. So that reduces it another 10%. So now you lost 15% of your radiation altogether. Then when you switch into the drums, you have a sudden change inside, and we will show that in a little bit second. And then you start charging your drums. So now you have hydrocarbon vapor as your upper phase, and then you have your resid foam as your lower phase. And then after you switch out of the drum, you go through your steam quench, water quench, unheading, and drilling, which all of those have the unique conditions and stuff as well. And then you start seeing how much does it change just in the vapor density itself. So to show that a little bit, I'm going to show you this. This is a 3-day trend of a coke drum cycle. I'm not going to really go over exactly what the level gauges are doing here. I'm going to do that a little bit later on. The intent and purpose of this is to focus on one cycle, and you can see that all these ones are set to a % change in radiation. So just to give you a frame, here you have 3 level gauges and you have a top density point. So you see all of them are changing to almost the same percentage until the level starts interacting with the detectors. So at point 1 is when you do your steam test. You go from 0 up to a certain value. So that's just you emitting steam inside the drum that causes all the detectors to lose a little bit of radiation because now you have mass in between the source and the detectors. Then you do your back warm. You see this nice exponential curve come up until it stabilizes. This is your overhead vapors from your online drum being fed back into to warm up your drum. And then right when you switch the drum, you see this unique. It is very unique that you see this almost every single time. Has a sudden rise and change, and then it comes back down. So you sharply lose a lot of radiation, and you gain a little bit of radiation back. What this is showing you is during that time that you are backfilling the drum, backwarming the drum, that vapor is giving off its heat to the drum walls and it's condensing. And so you basically have a pool of condensate in the bottom that you drain out as you're backwarming. But right before you switch, you got to close that drain valve. And so when the hot reset hits this, it all flashes. So when it all flashes, now you have a heavier vapor state inside this drum, which shows you that you do lose radiation. So as you increase on this chart, you're losing radiation, and then it stabilizes to a certain point. So you gain a little bit of radiation back again, and then it stabilizes. So this is where you want to be able to calibrate your level system for that conditions in that drum cycle, for that drum cycle, when the level gauges are basically stabilized in this area right here. So then as you're charging the drums, you see the vapor density gauge stays relatively constant throughout. So that means you're not longer changing any vapor state throughout the drum cycle here. But then you switch out. So when you switch out, you gain a lot of radiation again. And then you start doing your steam quench and water quench. And then you start seeing small changes. And then it gets up to where the water level gets above the coke bed. And then you drain it back out. So here's another very distinct part of the cycle that has its unique calibration conditions. And then you have your drilling, unheading and drilling of the devices. And they basically just seeing the change of radiation due to the drill stem passing back and forth in front of the radiation in the detector. So that's different process conditions, but then you also can have possible buildup issues. We're going to talk a little bit more about this as well too. Since this is a batch process system, coke can coat the sides of the drums. The coke cutters might not have time to polish the drum. So once they get done cutting the drum out, they typically like to go back and polish to make sure they remove any of the coke that might be hanging on the side of the drum walls. They might not have time due to hardness of the coke, time doesn't allow, or other issues that might come arise where they don't have time to do it. The reason this is important at this time is that if you ever started a cold drum, you can have a really high foam front inside. So operators have been taught that if these level gauges are reading 10, 20%, treat that as foam. Foam is up in this area. So they inject anti-foam to help try to squash that foam level down. If you have coke buildup on the vessel walls there, that would actually indicate a 10 to 15% change too. So they would see that and interpret that as foam level inside the drum. And when that foam level is in, they're going to start trying to inject anti-foam to try to squash that foam, even though there's not foam inside. It's just buildup on the side of the vessel wall. So you have to measure that and account for that to make sure that you're not wasting anti-foam. So how are nuclear gauges? What do we do? What's our solution and how do they all work together? So our typical arrangement that we have is sources on the outside on the vessel. So we typically use 2 to 3 fan beam point sources on the vessel. The number of sources and the size of the sources is directly related to the vessel diameter, the wall thickness of the vessel, and how long of a measurement span that you want. Each one of these sources typically have a 45 degrees. So if this is an 8-meter drum diameter, 25 feet, 26 feet in diameter, it can cover a 26-foot area range. But as the wall thickness gets thicker, if you get 2, 2.5, 2 3/4 inches thick, that starts getting attenuating more radiation, especially on the bottom part. So you might have 45 degrees, but it's only affected to like 35 degrees because of attenuation of going through the extra steel at a 45 degrees. So we do all the calculations to determine how many sources we need. And like I said, that's based on the drum diameter, the drum wall thickness, and how long of a measurement path that you want. And then you have your continuous level gauges on the opposite side. So that could be anywhere between 8 meters to 30 meters. So we can do this the top half of the drum, or we can do the whole tangent to tangent system. Typically, I like recommending 1 to 1.5 times the drum diameter. So that means if you have an 8-meter drum diameter, I normally recommend 12 to 16 meters of level measurement. The reason why I say that, that gives you the best controlling schemes that you can do to see what's going on inside. So for a rough example of that, if you only have 1 meter up here and your level's here and you inject anti-foam and that foam level drops below the 0 point, how far below 0 does it drop? I don't know. I can't tell you. I can't measure it. So you can't come up with any other type of control schemes and understand exactly what's happening with that. So that's why I like having at least 1.5 to 2 times the drum diameter so you can see what's going on here. And I also like going to the top tangent of the vessel because this way it's always important to understand what's going on here. This is where you can come up with the control strategies and stuff to make sure that you don't foam over. If you stop at this point and you get to that point, how far above do you go? You don't know because you can't measure it. I always like going to the top tangent. So this is just some pictures of installations. Here's our detector. Here's our sources. So our detectors, they come up to 8 meters long, each individual detectors, and we can sum them together to give you long measurement ranges, like I said, up to 30 meters. They're very sensitive. That allows us to use very, very low source activities. The one thing that I want to talk a little bit later on as well too is this function called XIP, X-ray radiation interference, X-ray interference protection. So we have an internal algorithm that takes care of that. And then we have a patented gain control that uses cosmic rays to make sure that over the life of the detector, the drifting of the PMT is taken into consideration. So we take into consideration of the source decay of the source, long-term drifting of the PMT due to aging, so you don't have to redo calibrations due to that stuff. Only thing that it has to be recalibrated is for process conditions inside the vessel. Then we have a top density gauge that's mounted inside on the side of the vessel. To me, this is the most important gauge that you have on the drum. It does multiple functions. So we like to mount this as high as possible, and its main purpose is to measure density inside the drum, the vapor density. So to go back to this chart, this is another chart, but it has exact same functions that you've seen before: cold empty drum, back warm, switching of the drums, stabilization. So during this time frame, you see the vapor density is changing, which is this yellow line. The vapor density is changing greatly, especially when you switch out. So if you do not have a way to measure that and to take that into account, when you switch out, the level gauge is going to see the drop in foam, but it's also going to see that a decrease in vapor density as a drop in level as well. So you need to be able to measure that and correct for that. So what do? We put this density gauge at the top to measure that density inside. It's connected to the level gauges, and that correction automatically takes place. So I got some graphs to show exactly what's happening. So here is a level system. You switch out right at this point. So at this point, the level is dropping, the foam level is dropping, but also that vapor density is decreasing. So it's getting more radiation, and more radiation to a gamma gauge equals a lower level. So it's driving the level relatively low. So here you're going from about 80% down to about 20%. So that's a 60% change. So this is what the vapor gauge was doing at that time frame. Pretty steady, about 25–30%. And then it creeps up to 40% here, and then you switch out. You go from 40% down to about 5 to 0% at this time frame. So this is what is being changed with vapor state. So this gauge is seeing that change in vapor and calculating into a level. So by using gas property compensation, we can use that information to adjust the level. So therefore, the blue line only really sees the change in level due to the foam collapsing. It does not see that change in level due to the change in vapor density at that point. So this is the corrected value that you would get to the DCS, and you can actually see where the coke actually ends up at. Another thing that you can use, since it's up here, you can use it for a high-level shutoff for water when you're doing your quenching. So if you look at this, the red line is the continuous level. The green line is that top density point, and the blue line is your water. So you see it ramping in. And then once you get to a certain point when that level switch comes in, you see it switches the water pumps off. So you don't accidentally lose track of it and overflow your drums. Then one of the biggest things I think that it can be used for is to monitor the particulate matter carryover. So what we're talking about in particulate matter carryover is as you're coking, you have this foam on top. I call it a popcorning effect. As a foam is disengaging, as the gases are disengaging from the foam, you have particulate matter that comes with it. If you're down lower inside the drum, gravity has enough time to pull those particulate matters back down. But as you get higher and higher in the drum, it has less time, and more of it actually gets carried through the overhead outlet nozzle and downstream. So let's look at this trend here. Here you see a vapor density gauge running about 30% the whole time, which is what you expect to see, because the vapor density should not change because it's about the same temperature, about the same pressure, same chemical makeup. So you expect the vapor density to be relatively constant. But you see right here towards the end, you see it tailing up. This increase on this tailing up is how much particulate matter is being entrained. And this goes down and coats overhead lines, and it can clog the fractionation strainers and actually ends up in the fractionation lines as well too. The amount of carryover is directly related to the height of the level in the gas velocities. The higher gas velocities you have, more carryover you're going to have. So people who are operating low pressure drums are going to have higher gas velocities, and higher gas velocities means higher foam heights and then also higher carryover. So you can use this in conjunction with the continuous level system, so you can basically have the best control scheme. So we had one refiner that was safely getting to 92% on the continuous level reading, but they noticed that they was having a problem with the fractionation. So they did a 6-month study where they wrote down what the continuous level gauge was reading at switch out, what the vapor gauge was reading at switch out, what they were reading when they did outage measurement, and so then they can calculate how much foam was at the end of the cycle, how much carryover they had. And what they noticed is that on the days that the density gauge got above 40% is the days that they had problems with the fractionation tower. So they correlated that data and said that always equals when our level is reading about 88, 89%. So they made the limit, instead of 92, 93%, they made it 87, 88%, so they can minimize the amount of carryover that they have. So here you see a week-long trend. So this is a 7-day trend. This is your overall level, and this is your vapor gauge. So you can see the higher that you read in your vapor gauge on your continuous level, the higher the vapor gauge reads. So this means you have more carryover at that time. So you see it's very proportional to that level over time. So another function that this gauge can do is to help monitor for buildup, for dome cleanouts. So when you're drilling the drum, you typically have a high limit switch located alongside of the straight line side of the vessel wall for safety purposes, so the drill stem does not come out with high pressure water. So coke does build up above this point. And over time, this coke drum, this buildup increases. So you see on this 252-day long trend, you see it's constant. Each one of these loaded spikes is a cycle. So you see it's pretty constant, and then it builds up, then it gets constant a little bit, and then it builds up again, and it builds up. Some refiners do not do a dome clean out, only when they need to. Some people do it on every single cycle. What this is letting you do, you can actually see that build up over time. So then you can bypass it when you need to and clean that out. Sometimes this buildup does fall off on its own due to thermal shock when the vessels is not warmed up correctly. So then that thermal shock will cause that coke buildup to loosen and fall down. You see it as it builds up, you can see it, and then here's a picture inside of the buildup in the upper dome through the overhead line. So you can see it actually does build up on a donut per se. So here's another trend at the same location where you see it step by step. Each one of these things happens to be a cycle, and so you see it's slightly higher than the cycle before because the buildup is slightly thicker. So here at this point, they do a dome clean out, and you see it goes back down to a minimum value and starts building up again. So it takes about 30 to 40 minutes to do a dome clean out. So if you don't have to do that every single cycle, you can apply that 30, 40 minutes to preheating and warming up your drum. So less thermal shock on the drum equals less stresses. Less stress means longer life of the drum. So we talked about the continuous level and now the top density. Now we also have a bottom density point down at the bottom that controls auto-calibration. When we do this auto-calibration function with an LB47X, it gives us the ability to do an outage measurement. So what this basically does, it starts and stops the calibration. So if level is below this point inside the drum, it tells the level gauges to calibrate themselves with the information that they have. How much radiation are they seeing currently at that moment in time? When the level reaches this point, it tells it, say, this is the information you use for this cycle, because this is the most current information that you have, and it calibrates this system. So then you also have an outage measurement. So it uses the same raw data, but it just calibrates it and conditions it in a different way. So you have a 4 to 20 back to the DCS for the overall level while you're coking, And then you have a 40-20 that tells you what the level is for outage measurement while the drum is deheaded under atmospheric conditions. So like I said, coat can coat the side of the drums if you don't have enough time to go ahead and polish your drum. As that coat builds up inside the drum, it causes calibration issues. So when you switch into the drum, they would start reading higher than actual level. So instead of being 0, it might be 7%. Next cycle might be 12%. Third cycle from then, it might be 3%. It depends on how much buildup you have on the side of the walls. And due to the large diameter drum, if you do have any small changes in your feed, so if you're going from M100 to Arabian, whatever type of oil, that is going to have a slight difference in density, how much fractionation that you're going to have. So that small changes in vapor density equals a large change in radiation due to the large diameter of the drums. So this just makes sure that it reads 0 and it's calibrated for each individual cycle. Each individual cycle is completely unique and different from another one. So this is another graph that you can see with the calibration, how it changes from cycle to cycle. So you see it all has this very unique sudden increase when the level comes up and comes back down and stabilizes. Every single cycle does that. So on this one, it stabilizes here. So this would be the calibration point for this drum cycle. The second cycle, this would be the calibration point for this drum cycle. And then this one would be the calibration point for this drum cycle. So what it's doing is that it captures this point to be the calibration for the detectors during this cycle. And then it resets itself. And then for this cycle, it selects this point. So it automatically adjusts itself at the start of every single cycle to make sure that you get the most accurate and most reliable measurement for that individual cycle. So I'm going to talk a little bit about the outage measurement. Outage is measured from the top of the flange down to the coke bed. It used to be done manually with a plumb bob. You go up and you throw it, basically tape measure with a weight on it, and how far does it go down. Now with automatic unheading devices on top, it's getting more and more difficult to get to this area to do that manually. So a lot of people have turned to the drill stem where they use a potentiometer and a take-up wheel to basically see how far the drill stem has traveled. And once the drill stem hits the coke, they look at a potentiometer strain gauge and see the weight being taken off. The problem is sometimes this coke appears really light and fluffy, and that drill stem can penetrate 2 to 3 feet, 0.5 to 0.8 meters into that coke bed before it would take up the strain. So you're not really getting a true accurate measurement. And then talking to my friends at FlowServe, they have problems with people. Ports get plugged, O-rings can get damaged, and like I said, the measurement is not 100% reliable. It depends on how far that weight of that drill stem actually penetrates the coke. So what we do is that we take the same information and condition it. Why can't we just use the same measurement that we have while we're coking? Well, while we're coking, it's calibrated for a lower phase of being molten resid foam, and the upper phase being hydrocarbon vapor. During the outage phase, the lower phase is coke, hardened coke, and the upper phase is atmospheric, maybe a little bit of steam. So when you switch from the coking condition to the outage condition, the lower phase density goes from molten resid, which is lower than the coke. So that density actually increases as you go from the coking to the outage cycle, phase of the cycle. And then the upper phase goes from a heavy hydrocarbon vapor to atmospheric. So it decreases. So they go in opposite directions. Another reason why you can't use it is the geometry is different. While you're coking, the foam is more like a dome. As you're feeding it from the bottom, it bubbles up and rolls over. It's kind of like a continuously erupting volcano, basically. So here we are tracking the level at the top of the foam while you're coking. On an outage, the coke bed is a little bit of a concave measurement. So this is where we have an advantage of being a cross-sectional average inside the vessel, is because we don't really track the level at the very top. We don't track the level here. We track it someplace in the middle because we need a little bit of this phosphorus material to absorb that radiation. So these are the two reasons why that the outage system is never going to be exactly dead on accurate to give you an outage measurement by using the coking level. because it's calibrated and conditioned for a completely different part of the cycle. So to show you what that means, here's a trend. So the purple line is the outage measurement. The yellow line is the overall measurement. So you see while you're coking, there's an offset. Here they hit it with anti-foam, level comes down, level goes back up, you switch out, you do your water fill, drain, and then here's your outage. So let's zoom in and see that. So here, your outage is measuring here. So this is a pretty good, because it's calibrated for this conditions here. This one is calibrated for the coking conditions, but using that density gauge to try to calculate and adjust itself. So if you wanted a more accurate measurement, you take the same information and calibrate it for that condition of that cycle. So another thing that we can do is put a target gauge out there. A target gauge is a second independent verification of where the level's at. It has no other purpose out there besides being a level switch. So the one thing to help people to transition over from neutron backscatter gauges to gamma continuous is recommending putting the gamma points at the exact same elevation as the neutron backscatters. One advantage of the gamma continuous is wherever there's the radiation field is at along the length of the continuous, you can always add a point, at that location. So this helps simulates what the output would be for the neutron backscattering, gives operators some confidence and some familiarity that this is what they're used to. So I have a little bit of an animation here to show you how all the things work together. So over here, you're going to have the drum level change, and this is the trends. So I'm going to briefly describe what the lines are. This light blue line is the vapor density gauge at the top. The dark blue line here would be the bottom auto-calibration gauge. The red line and the orange line are the top and bottom level gauges, respectively. The green line would be the overall, which is the summation of these two gauges together. And this purple line is the output from the switch, and that switch is located at 56%. So as you start your cycle, the level system is staying zero because this part has full amount of radiation. So it's keeping the level system reading zero at that point. You see the foam level is increasing over time, getting higher and higher and higher. And once it gets to this point, his bottom detectors start seeing the radiation. So it's telling the system to go ahead and start tracking the level now. So now they come off of zero and start reading the level. So as foam gets higher and higher inside the drum, you can see it. As you approach where the split is between the low and upper, you can see that when this one reaches 100%, the top one starts reading. And then when the switch comes in at 56%, my level is about 55, 56%. So that just tells you my level system's reading correctly. Now I hit it with anti-foam, my level drops. I keep going a little bit more. I switch out of the drum, my foam level drops. I start doing my water fill. Once the water level gets above the coke bed, you start tracking the water level. And then that's the end of the cycle. So that's how they all work together, so you can track the level, either it be water, coke, or foam. So why do you want to use gamma continuous? What advantages do you have on that? So the one thing, it does help you increase coking capacity. It increases the reliability because you can have a better idea of what's happening with the foam inside. And then you can also use it to help optimize anti-foam usage. So let's dive in over this a little bit more. The continuous level is not just points. You know where you're at all times. With the neutron backscatter, I know I passed the 7-meter neutron backscatter, but I'm not at the 4.5-meter one yet. Where I'm at in between, I don't know. So this, you can determine rates of change. You can see how fast it's coming up, how slow it's coming up. So you can make some predictions and stuff as well too. So this is the one biggest advantage of the gamma continuous. And since you are not predicated to exactly where these things are mounted to the drum, say, hey, I want to increase my target where I want to switch out up 2 feet up. I'm still measuring this area, so I can increase my target 2 feet up. With the neutron backscatters, you have to guess, I'm I'm above this point, but not to this point yet. Where I'm at in between it, I don't know yet. So by using the continuous level, you get better drum utilization. What I mean by that is that you can actually fill the drum up higher. So I had a customer that was able to go from an outage of 24 feet to 17 feet, and they increased the cycles from 12-hour cycles to 14-hour cycles using the same feed rate, because they had a lot more confidence in understanding exactly where the foam front was, what the foam was doing, and where the level was going to end up. So they was able to increase and go higher inside the drum. So another thing that you can use to see is that rate of change per se. So here you have anti-foam injection, and here you have anti-foam injection. So they look slightly different. So what's happening at this point, if you look at this and do a propagation, they turn anti-foam on and shut it off. Once they shut it off, that foam level comes right back to where it was, almost like you never injected anti-foam. So was it really useful to add anti-foam at that time and shut it back off? That's the stuff that you can do. Here you turned it on and left it on, and you can see it quashed it, and now the rate of change has decreased versus what it is over here. So here's another one that's done some anti-foam injection. So you can see they turn anti-foam on for 15 minutes, shut it off for 15 minutes, turn it on for 15 minutes, shut it off for 15 minutes. So they did that over a period of time to see if that does any influence on not only how the coke sets up, but in stuff, how much anti-foam they end up using. So here's one location. So you see the white line is the anti-foam turned on. The black line is overall level. So when you turn anti-foam on, it drops a little bit and starts to continue. They turned it on and left it on for the whole time. So what you can do, you can calculate the area under the curve to figure out how much total anti-foam that you use. So in this one, it's 325. So they did a little bit different one on this cycle. So you can see here's the overall level. Hit it with anti-foam, level drops, comes up, and they turn it off. So the area under this curve is only 200. So you see they greatly reduced the total amount of anti-foam that they used here. So here was another scheme that they had where they tried ramping it up. They ramped it up to about 30% flow, let it run for a while, ramped it up to about 50% flow, 60% flow, and keep ramping it up and see what kind of effect it had on continuous level. So the area under this curve is about 201. So it's about the same amount of anti-foam, total anti-foam that you used on the prior one. So the continuous level systems increases measurement reliability. Some of the issues that people had with the neutron backscatters was that they was mounted to the drum. When they mounted to the drum, you have to remove the insulation. So that allows a lot of heat to get to the detectors, and everybody knows heat is not a good friend to electronics. The reason why the insulation had to be removed is because if the insulation retained water, the neutron backscatter gauge would detect that water and the insulation and read higher than actual. So remember, I was also talking about how the neutron backscatters only measure a small sphere of influence inside a vessel. Sometimes you can get vapor channels that build up alongside the vessel wall inside. So customers were complaining that the neutron backscatter gauge worked the cycle before, but it didn't work this cycle, but it worked again the next cycle. I don't understand. It's not a function of the neutron backscatter gauge not working. It was just telling you during that cycle, you had a pocket of gas, a channel of gas that happened to build right in front of that neutron backscatter. So it's indicating what was in front of it. It doesn't go all the way across the vessel. It only gives you a small little area inside of the vessel. And other people, if they're in areas where it rains a lot, they do have a problem where water cascading down the side of the drum or anything like that. Sometimes they put rain shields on top of these things because they will end up reading 15–20% with water cascading down the outside of them. So the water cascading down the outside of a drum does not affect the gamma continuous gauge. So, and of course, as I mentioned, there's no radiation due to the high dose rates around neutron backscatter. So if you can Reduce the chances of foam overs. Foam overs are very, very costly. The unit could be down for 2 to 6 weeks. You have to go in and manually clean out the overhead lines and sometimes fractionation tower. That could be as high as $2 million. The worst thing about this is while you're cleaning, the coking unit is down. The coking unit is down, you're no longer making your high profit margins and stuff. So, and then if you can greatly reduce your anti-foam, not only are you reducing your chemical costs, it also helps you to maintain inventory management if you have some type of DCS control, either on, off, or flow rate control. Because a lot of times I go to customer sites, they always have one shift or two shifts that uses 2 or 3 or 4, 10 times more anti-foam than the other shifts. So it's hard for them to manage exactly when they need to order it and stuff, because one shift is using a lot more than the other ones. And then also it is a poison downstream. The hydrotreated downstream from a hydrocracker, all that silicone ends up going down and it poisons that catalyst. So it doesn't really affect the delayed coking unit, but it does affect overall profitability of the whole refinery if you have to replace that catalyst more often due to the carryover. So I'm going to describe some information about how the neutron backscatter gauges and the gamma gauges work together. So out of the literature of the neutron backscatter, they typically say hydrocarbon vapor reads 0 to 25%, low density foam 25 to 50, high density foam 50 to 75, coke 75 to 95, and water 100%. This gives people the misconception that as your foam is filling up inside the vessel, it's going to give you a stir step effect. But what really happens is that since you're only measuring in the sphere of influence, you get a gradual change of hydrogen in that area. So basically what you get, this is a neutron backscatter, and this is a neutron backscatter, this purple one. So let's zoom in and see on this thing what happens. So you see it goes from a minimum signal to a maximum signal, and it does that over about a 1 hour period. So where in this trend do you have high density foam, low density foam, or anything like that? Because what it's doing, it's averaging the overall amount of hydrogen it has in that 3-foot area per se. So here's another one. This green one's a neutron backscatter. This one's a neutron backscatter. So this one happens to be located at the same elevation, 7 meters down from the top tangent. And on this instance, it goes from a minimum signal to a maximum signal in 35 minutes. The reason why I'm showing you these response curves is so you can look at them and understand by replacing those neutron backscatters with a gamma point, with a gamma density, you get almost the exact same output over the same amount of time. This is a 45-minute to 60-minute output. This is a 45-minute to 60 output where it goes from a minimum signal to a maximum signal. So this is measuring the radiation over the neutron radiation over about 800 millimeters, about 3 feet, 4 feet of measurement. This is measuring the radiation over about 2 inches, 50 millimeters. So you can see that it has about the same amount of output. So on foam levels, the one thing you have to understand when you have both neutron backscatter and gamma continuous on it, when I'm looking at my outputs, is level going up or is level going down? So what do I mean on that? So the readings don't always match between the neutron backscatters and the gamma continuous. A lot of people complain that if this gauge is located right here, that is 55% of my overall span. So when this thing reads 100%, my gamma gauge should be reading 55%. Well, that's not always the case. That's due to the foam height and the foam density. So let's see what's happening here. So if this one's reading 50% because it's reading the foam, this is reading light density foam, this part's reading heavy density foam. So it's reading 50% basically. My gamma gauge is reading 70% because it's reading up here. You hit it with anti-foam, that foam level drops. Now I have more hydrogen in front of my neutron backscatter gauge, so it's reading a higher output. It's reading 70% now, but my gamma gauge is reading 60% because my overall height has decreased. So I have a little bit of an animation to help show that, help prove that point, not really prove that point, but demonstrate that point. So this green bar graph is the output from the continuous level, so it's tracking the level This green bar graph would be the output from the neutron backscatter gauge here. So you see it has a little bit of hydrogen in front of it due to the hydrocarbon vapor and a little bit of the foam in front of it. If I hit it with anti-foam at this time, my level drops. So if I squash that level down, that's actually increasing the hydrogen in front of that neutron backscatter. So this neutron backscatter is indicating more neutrons, more hydrogen. So the output for that one goes up, even though the overall level goes down. So this has an issue with people not understanding the system. When they see that one level system goes up, one level system goes down, which one do I believe? Well, the answer is both, because both of them are right. Because this is the neutron backscatter, is not a level, it's the hydrogen density gauge. So let's look at a trend when this thing happens. So this yellow line is a neutron backscatter, and this yellow line here is the gamma continuous. That's the bottom gamma continuous, and this is the overall, this red line. So let's zoom in and see what happens. Here you inject an anti-foam at this point. Inject anti-foam, foam level drops. But what happens at this point? My neutron backscatter gauge goes up, but my gamma continuous gauge goes down. Why is that happening? Because like I said, that foam level is basically being squashed down, so that hydrogen is concentrating over a smaller area, which means the hydrogen density is increasing, which is exactly what the neutron backscatter gauge is showing you. So when they turn anti-foam off, the exact opposite happens. The foam level pops back up, so my gamma continuously increases, but my neutron backscatter gauge decreases. So as that foam expands over a larger area, the amount of hydrogen in front of that neutron backscatter gauge actually is decreasing. And then when they hit it with anti-foam again, the exact same thing happens. My neutron backscatter gauge goes up, even though my gamma continuous gauge goes down. This time they leave anti-foam on, and due to the constant feed of the drum, now both neutron backscatter gauge and the gamma continuous both are increasing at that time. So by looking at the foam height and the foam density, one gauge be going up, one gauge be going down. Where this is really critical to understand this principle is when you have a foam over after you switch out of the drum. So we're going to cycle in on, focus in on this part. So at this dotted red line is when you switched out of the drum. So to explain these trends up here, this is your top neutron backscatter. The light blue is your second neutron backscatter down. The red line is the gamma continuous overall level, and this white one is your vapor density, the top point. So right when you switch out of the drum, my second neutron backscatter gauge increases, because if you saw the animation, my level is slumping down. As my foam level drops down, the hydrogen in front of that second neutron backscatter gauge is increasing. So it's actually going up. My first neutron backscatter gauge went down because now the foam is no longer in front of that physical elevation. So it's measuring hydrocarbon vapor now. So it goes down. My gamma continuous goes down, and my vapor density goes down. Now, a little bit later on, the foam level comes up. So when it comes up, at that point, now my second neutron backscatter gauge comes down, because now my foam has expanded over a larger area. So the hydrogen in this area of that foam has decreased because it's spread out over a larger area. My first neutron backscatter gauge goes up because now it has foam in front of it, whereas before it did not. And then my gamma continuous gauge also goes up. Then when you get to the point where the foam level is actually collapsing, now my second neutron backscatter gauge decreases, or goes all the way to 0. My first neutron backscatter gauge decreases, goes all the way to 0, because the foam level has dropped below where they're physically located on the drum. And then my gamma continuous gauge also drops. So here you have, it confuses operators, especially during a foam over, is that I got one level system going up, one level system going down. Which one do I believe? Well, their answer is both, because one is telling you the foam density is decreasing because the foam is expanding over a larger area. So now we're going to go in the last part, which is issues that you might have with gamma continuous. So some of the issues that you might have is mounting, heat, crosstalk, and NDT radiography. So when you mount things, we like to have these things mounted about 300 to 600 millimeters off the drum. So when you look down, you have a nice clear path. If you ever been out on the side of a drum, the heat comes off the side of the drum and creates a natural updraft. So if you keep these things relatively at a pretty good distance, 300 to 450 millimeters off the drum, 12 to 18 inches, that updraft here has a natural cooling effect on the detectors that prevents them from overheating. One thing that we don't want to have is when we have what we call crosstalk. That's when the sources and detectors align in such a way that radiation from one vessel can interfere with another vessel. We don't want that to happen. So to give you an example of what happens when that does that, so here these two vessels are pointed at each other. You got your detectors in between. So if my level was to change on this vessel, my level decreases, I have more radiation to this detector. Well, this detector sees more radiation as well too, because it keeps traveling from this one over to here, and my level actually decreases, even though it's the same level as before. And vice versa happens after the fact, is that when my level increases, this detector loses radiation, but this detector also loses radiation, and so you have that influence from one vessel to another vessel. So when you look at an overhead shot of a delayed coker, this is a 4-drum coker. Here's your vapor outlet nozzles in between here. So you're going to have them aligned, trying to maximize this space at 45 degrees. Here, these drums, these detectors might interfere with each other because the sources are pointed toward each other. So you kind of try to minimize that by rotating them around the drum a little bit. So this minimizes how much interference that this vessel has on this vessel. But if you can, this would be greatly ideal to do that. That way you minimize it all together. You know for a fact they have no influence on it. So another issue that people talk about a lot of times on delayed coke drums is radiographic or NDT testing. The reason that is, delayed cokers tend to be the highest structure refinery, and the level system happens to be on the top half of it. So if you can see those detectors and you put a source out there, those detectors can see that source because there's nothing in between the source and detector to absorb that radiation. So some typical size radioactive sources they use for NDT testing is cobalt-60, iridium-192, and selenium-75. So they have to determine what size capsule to use, what energy to use, by what are they X-raying. Are they X-raying a pipe? Are they X-raying a vessel? What's the wall thickness? What kind of detail you need? What kind of resolution you need? That determines which one of these ones that you use. To give you a frame of reference, these are relatively large activities. So a typical one for cobalt, 50 to 100 curies, iridium-192, 100 curies, selenium-75, 40 curies. We might use anywhere between 1 to 3 curies on the larger drums on the delayed coker, and they're using 50 to 100 curies. So they're considerably larger than what we're using. So what happens on our system is that you have radiation coming from the back side. These detectors, as I mentioned before, don't have spatial resolution. So they see an increase in radiation, so the level will drop when they see radiation from the NDT source. So to give you a frame of reference, so on a typical 2-meter gauge, we might have an average radiation field of 0.5 microsieverts per hour with a detector sensitivity of 10,000 counts per meter. So that gives us a total count rate of 10,000 counts per second. So to calculate what the radiation field is at from a point source, you use this equation, which is the gamma constant times the activity divided by the distance squared. So I did the math for you. So for a cobalt-60 source, 100 curies, it puts out of a 0.5 microsievert per hour field. Remember, this is the same radiation field that we put on the detectors from our sources at 1,652 meters. So it puts out a 0.25 microsievert per hour field at 2,337 meters. So that is quite a long ways away. So at 1,652 meters, that's enough radiation to drive the level system from 100% to 0. This is enough radiation to drive it from 100% to 50%. So what does that look like? So for iridium-192, the distances are 1,098 meters and 1,553 meters. So what does that look like? So here's a picture of a refinery that we have. Here's our delayed coking unit right here. So if anybody's doing any type of NDT testing within this radius, that could interfere with the level system on your delayed coker. So you have to keep in mind that a lot of places have procedures in place where if there's doing any type of NDT in the plant, that to let all the operators know. This is showing you, and this is not the case, but let's say that this is a refinery over here and they're doing NDT testing. They could be affecting you even though they're way over here. So they have no obligation to let you know. So you could do some steps and stuff like that to help minimize how much issues that you have with this. So, so this is just how much shielding requires for that. So most places have what they call a laydown area where they do a lot of pre-welding and pre-assemblies and stuff like that. So in this refinery, the laydown area is located here. Here's my coke drums here. So if you know that, when you go to install your detectors on your system, by looking at where my laydown area is in relationship to one of my detectors, if you mount the detectors on the back side of the drum, and you know a lot of NDT testing is coming from this direction this way, the drums can act as a shield and you can minimize a great deal of the issues that you have from NDT by putting the detectors on the proper side of the vessel. If you would happen to put the detectors on this side of the vessel, they would see that NDT testing sources all the time because there's nothing there to absorb that radiation per se. If you happen to be in a position or a situation where you cannot do that because there's NDT testing all the way around, remember I mentioned at the beginning that we have something called X-ray interference protection, XIP. So this is an algorithm that we run internally of our devices. Basically, this is our measurement signal. This is the instantaneous radiation that we're getting from our sources. So we calculate a threshold limit, right? A certain noise band above that per se. So if we see a sudden change of radiation outside that noise band within a certain amount of time, we know that's coming from an outside influence source. So what we do during this time frame is that we freeze the output value, so it does not let it go to a minimum value, and we look for it until it goes back into that threshold band, and then we unlock it and start continuing measuring the level again. So this is a great advantage because we do this internally without the need of an extra detector on the outside of the vessel and stuff. So those are some issues that you might run across, is a little bit of the mounting issues, XIP with the X-ray protection and stuff. So to summarize, so by using the coke drum continuous level, you can increase the throughput through the unit, help increase the reliability unit to help minimize the amount of foam overs and stuff that you have, maximize the use of your anti-foam so you can use less of it so you don't have the chemical cost or the poisoning of the catalyst downstream. And the biggest thing is to prevent foam overs. If you can reduce that foam overs, that's the biggest money loss that you can have in the delayed coking unit. And then for operational thing is to minimize that carryover. You can minimize that carryover, you're gonna have a lot longer run time between having to shut down and clean out your overhead lines and your fractionation tower. So that is the end of the presentation. And so I will open up any questions that some of you might have.
David, there's been a few questions. Thomas has answered a few in the meantime. There's more in the Q&A. Wait, there's a few more coming in.
Yeah, I'm reading it right now.
Okay.
Timeline is a possible copy of this. Yes. I can talk to you later, Rich. I can call you sometime, either tomorrow or next week. No voice. I cannot hear the presenter. Oh, I didn't.
Yeah.
Any connection between Berthold technology and Berthold rays that bombarded the surface? No, not really. Yeah, get a copy of it to PLC.
Yeah.
Yeah. So how far can you mount the source? That's really hard to determine because it's really hard to predict the scattering that you might get off the surface of the vessel. That's a function of the distance of the source from the shield itself from the vessel, what is the radius of the vessel itself, and what is the collimation angle as it comes out of the vessel. So that's really, really hard to say as a general terminology, but if you have a specific example, we have a better guidelines to help you with. So Thomas answered that question. Any impact of the normally occurring radiation? Typically, we don't see that much issue with norm when it comes to delayed coking. I have never ran across that. I have run across that in other applications, especially in PDH units and polypropylene. Yeah, that's what I was talking about. Most people, when they walk around these sources and stuff, they might be near that source for 2 to maybe 5 seconds. So all those values I was given to you was in per hour. So if you divide that by 360, that's how much dose that you get, and so it's relatively small. So Pablo Gonzalez, how you doing, Pablo? Is it possible to shield the detectors with lead? That depends on the type of source that they're using. If they're using Cesium-75 or Iridium-192, yes, it is possible. But if you're using cobalt, it's not really possible to do that because the cobalt has such high penetrating energy. So what source do you recommend? Cesium-137 is typically the one that you get the maximum life out of it. Would a gamma point source always read the same at the continuous level? The gamma point source will be within plus or minus 2% of it because it's reading the same radiation versus what the neutron backscatter would be, because you're not dependent upon the foam height and foam density per se. What's the current typical, oh wait a minute, it just moved on me. Current typical configuration on a 32-foot drum, 3 or more sources. Typically on a 32-foot diameter drum, if we was to go to something like a 45 to 52-foot level measurement, that would probably be 3 sources on it because of what I mentioned at the beginning with the sources have a 45-degree collimation, but when the wall gets so thick, you really don't have an effective 45. You might have 35, 38 degrees effectiveness. So you might have to add a 3rd source to minimize, get the radiation all the way down to the bottom of the continuous level span. Any recommendation for moving sources and single point detectors to have special resolution along the drum? What kind of device could we use for a pilot unit? Freddie, I've talked to you before, Freddie. I think we can have a discussion about that. I have some ideas on that. What's the accuracy of the outage measurement by gamma alone? What could be done to improve this? Can you use a moving target switch to tune the outage? Are they easily removable? From my experience, the outage measurement, you can get that normally within about a foot of the true outage, and that depends on what you measure by true outage. Because if you remember in my presentation, I showed you where most of the outage, the coke bed is more of a concave. So if you are doing a manual outage with old plumb bob, you are basically hitting the lowest point because you're right in the middle of it. Whereas you have higher coke alongside the walls as you go towards the outside. So that's one advantage of the neutron the gamma continuous. It gives you that cross-sectional average. We're not giving the lowest point, we're not giving you the highest point, we give you someplace in between. So typically, from my experience, it's about 1 to 1.5 foot from what most people call actual outage. And the movable target switch, that's one thing that's nice. I mentioned before, you have, let's say, 15 meters of level measurement on the side of the drum. You can put a point switch any place along that 15 meters that you want, and you can move it over time. So if you want to start, my target switch is, I want to put it at 20 feet down from the top tangent. I'm going to hit that, and you feel safe over time. I can move that up to 18 feet. And that way now you just have to recalibrate it for that position and then move. And once you hit that and you feel confident and you want to move it to 16 feet, you can just move it up 2 more feet because you still have the radiation there. I like recommending to people when they mount those target switches to use flex conduit. And so that way you don't have to redo the hard conduit and redo the work all the time. So is the auto-calibration feature standard on Berthold models? Basically, we only use it in the coke drums things because that's one that has most amount of issues with the calibration because of the batch process. Do you know anybody has put detectors across the entire coke drum? You mean from tangent to tangent? Yes, we do. I've seen a lot of tangent to tangent coke drums, but to me, it's not really cost effectiveness because most of the stuff that's happening is in the top part of the drum. If you ever was to look at trends from a tangent to tangent level system, let's say that you have four 24-foot level gauges. The bottom one would be 100% within an hour, hour and a half. The second one would be up 100% in about 2.5 to 3 hours. And then the next 8 to 12 hours of the cycle, you'd be running in that third and make the bottom half of the fourth one. So the first two runs up relatively fast in maybe 3 to 4 hour time frame. So you really don't get much information out of those bottom two. I would recommend customers spend that extra money they're putting on long level detectors at the bottom part of the drum for switches and targets at the top part, because that's where it's the most critical, because you don't want to make sure that you foam over. But if there is any need that you want to try to do some type of study to understand feed rate changes, hey, what happens if we inject anti-foam for the first 45 minutes for an hour? Do we get a compacted bed? We can do stuff like that. But if you have an 8-drum coker system, I would probably recommend doing that on 2 drums, and then the other 6 drums is the top half. So during coke drum water quenching program, how to keep the drum pressurized, the entire program affects the load measurement. So when you keep the drum pressurized, that vapor vapor density gauge at the top compensates for any type of pressure changes inside, so it gives you an accurate level measurement. Is there any radiation that is detected above the source? How to compensate in the level measurement? Perfect. I mentioned a discussion with you before on this. So this is a tricky question. Not really a tricky question, but you have to fully understand a little bit more about what's happening inside of a drum. So if I am incorrect, Herbert, what you're asking is what we had a discussion about 10 years ago. This radiation, we always show the radiation coming out straight across and down at a 45. But in all actuality, this radiation leaves, once it leaves this container, it shines upward about 10 to 12 degrees. So in that case, this detector is seeing radiation from this source because it's coming up. So when you do get processed material in front of this part, this detector here sees a change in radiation. So we take that into account when we do our calibration linearizations. But I know that for the discussion we had in the past, you're not using long level detectors, you're using relatively small, short detectors cascaded together. And that way you can see that changes a lot more than normal, because you might be affecting 2 or 3 gauges with that shine up instead of only 1. So which international standard governs the radiation limits and other safety aspects and areas? Well, the 2 main bodies that are out there, the international one is IAEA, the International Atomic Energy Association, and then in the United States we have the NRC. But those just basically set the guidelines. Every individual country has their own standards, what the standard radiation limits are, what the exposure limits are. So everybody has to have their own. And then within the individual countries, operating companies can come up with even more stringent standards. And so you have to follow those ones as well too. So that's a tricky question to answer. If you tell us what country you're in, we can help you understand a little bit more better about your specific country specifications. And then if you have any corporate specifications you have to abide by as well too. So did I answer most of the people's questions that had the questions?
Yeah, David, as far as I can see, you've answered most of the questions. And if your question wasn't answered, we'll get back to you in the next day or 2.
And if you do have any more questions, go ahead and email us in. We can answer those questions and get back to you. If you have some type of specific question that you would like to have too, we can ask that as well too. So
yeah. So from my side, thank you everyone for attending, and we hope you enjoyed it. And please check our homepage or follow us on LinkedIn and Facebook for future webinars, information, whatever. And we look forward to seeing you again.
Okay, thank you, everybody.